Good afternoon. Good afternoon, everybody. We are back for the third of our keynote speeches. And I'm happy to say that Dimitar Jetchev, the CTO of INPHER, is actually with us. His information will complement what we heard already, and I'm sure it's going to be very, very interesting. So thanks to all of you, and I leave the floor to Dimitar. Thank you and welcome.
Thank you, Massimo. Thank you. So I'm sharing my screen now. I hope that you guys are seeing it, and I hope that everybody is hearing me.
Yes, good,
Okay.
loud and clear.
Perfect. So first of all, thanks for inviting me here to that event. So I know that you guys are primarily interested in randomness, random number generators. So my topic is, I should say up front, is slightly different, but you will see how randomness is used and what kind of randomness we need for the technology developed by INPHER. So INPHER is about 5 years old. Just to tell you a few words about the company, it's based in Lausanne in Switzerland and also in the US, in New York and San Francisco. So I'm going to start by the motivating problem. So obviously we talk about big data today, and we talk about data coming from different data silos, and we talk about privacy of data and so on. So you know that ideally when you're doing data analytics or machine learning, you would like to collect as much high quality predictive data as possible. So typically, if you have good data, then you could build good models. And also typically what happens is, so it's the quality of the data, it's just the access to more data and more high quality data that helps you essentially achieve better models with better performance. Typically, we're using very basic machine learning tools. So we could use regression models, or we could use decision trees. And nowadays, obviously, with the more compute, we could use deep neural networks. But in a sense, all of these models are performing based on what kind of data you feed into into these models. And nowadays, what happens is when we're talking about data privacy, so you're not always really accessing this data. So let's talk about privacy in a second. First of all, you have 3 types of data privacy that you could distinguish. On one side, you have securing data in transit. So here we're talking about secure protocols for communication. In the middle, you're seeing securing data at rest. So that means encrypted data that stays on disk. Now, on the right, that's the interesting and relevant part for essentially data analytics. So securing data in use. What does it mean? If my data is stored on the cloud and is encrypted, I cannot a priori compute or use the cloud to compute on that data. What I have to do in general is I have to take the data, probably download it at a certain server or data center, decrypt it, and only then do the analytics. Now, what INPHER is doing, INPHER is solving this problem. So INPHER is trying to produce a technology or a platform that allows you to compute actually unencrypted data. And here encrypted is very general and broad term. I'll tell you exactly what it means mathematically as we go on. But here is the company overview. Obviously, this technology is a very advanced, sophisticated cryptographic technology. So we have a strong team of security experts. We also have prior entrepreneurs and business development leads, and also, of course, data privacy, like legal counsels. So let me start with that. So the idea is the following. If you have a large financial institution, let's say, now this financial institution might have some local data in a given jurisdiction, let's say in Italy. So you name a bank that operates in Italy, that's a multinational bank. So this bank, suppose that they are interested in building, for example, a credit scoring model. So they could use the data that's only in Italy, only at that particular financial institution, but obviously this data will not be as predictive as if you add the data coming from all possible geographic locations where this bank is operating. So essentially, the idea is that if you aggregate all of these locations, then you may get a better model. But that's not even everything. Imagine that you could add an external institution having data for the same customers or having data for more customers that could potentially help you enrich your prediction model. Then what you see is a massive data improvement. So this is the idea of kind of secret computing. How can we computationally access this data, the entire ecosystem, so that we are able to improve our model? So AUC here stands for the area under the curve, as you might know, probably. So what's the obvious solution if you have two, let's say, data silos? So if you have two data silos and they hold private data, obviously I'm unable to aggregate this private data at a central location because the data is private, then the central location will see the data on both sides. So what we do instead, we use a cryptographic technology known as secure multi-party computation that allows us to do what we call secret computing. And in this slide, I'm going to show you the overall architecture of our platform. So our product is a platform. It's a security as a service. And it has three major components. So it has an analyst portal on the left, which allows you to operate the computation. In the middle, it has what we call an XOR service, and this is where the random number generator lives. And I'll tell you more about how it is used mathematically. And on the right, what you're seeing is a collection of XOR machines. So what this means is you have different private data sources, and each of these private data sources is running a virtual machine, INPHER specific virtual machine, that allows for a computation. So a computation that is a distributed and secure computation. The idea at the end of the computation is the following. So you want to make sure that you're computing a function on the aggregate of these data sources in such a way that the data analyst at the end sees only the result of the function and nothing more about the inputs A, B, and C. So you think of A, B, and C as being segregated inputs, private inputs. They cannot be aggregated together. Yet I want to take my function f, which is a public function that can be a computer program or algorithm or anything that you can code in a higher level language, such as Python, for example. And then you basically you evaluate this function on A, B, and C, but without seeing A, B, and C. You could imagine this as, for example, an Excel spreadsheet, and then you have just a description of one column, but you don't really see the values in this column. So that's what we do. So the first thing is the analyst is going to write the function f. So he's going to code the function f in some higher level language. Then our service is going to run a special purpose compiler. And after that, basically there will be some random number generation going on. And that random number generation will generate certain random data that will be used in the computation. After that, we basically detach the service, and what we do is we start the computation. That's here on the right. It's a distributed and secure computation, so there is a list of instructions that are executed by the machines. These instructions involve local computation and communication, and then the result is essentially broadcasted to the data analyst and is computed with high precision. Do you have any higher level questions so far on that?
Yes, I have one.
Yes,
sure.
Please.
So how do you ensure that the distributed computation is done correctly?
Yes, so that's a very good question. So there are various techniques, including zero knowledge proofs, certain types of zero knowledge proofs, so that without actually seeing this data, you could prove that the protocol has followed correctly on the input data.
And do you have any kind of ensure? So how do you ensure that the random? So I'm working on that. So how do you ensure that the random data that is generated by the distributed parties is truly random? And how do you make that?
Yes, so this we do have cryptographic techniques to do that. Essentially, we do have a technique to verify that the randomness follows the prescribed distribution, because the distributions that we use, they have very special properties. They have certain parameters. It may not always be, for example, the uniform distribution. You may sometimes want to generate sample a random number from a Gaussian distribution with certain mean and standard deviation. And that also we have a technique by essentially revealing certain triplets that are not used in the computation, certain random numbers that are not used in the computation, to validate that the distribution is the correct one. So you could always question the random number generators from the point of view of the data owners.
Okay.
Then the other question that I have, thank you for asking this question. The other question that came to my mind is about the computation itself.
Yep.
Because if you're running algorithms that are absolutely, say, you have the possibility to have an absolute parallelization is fine, but what if the result depends on correlation between data that are, for instance, stored in A, B, and C?
Yes, so I will talk about this.
Okay.
So for example,
sorry.
but that's a valid question. So for instance, if you have A and B and you want to compute the correlation between A and B, you could decide to reveal the correlation, right? You could decide to reveal the correlation, but then everybody knows that the correlation has been computed and revealed.
Okay. Yes.
So it is up to the parties to agree on the function f that is allowed to be computed on the data.
Okay.
For example, you could even, if you choose your function f poorly, if you choose, for example, the identity function, then you obviously reveal the entire data set.
Absolutely.
So you don't want to reveal that. So that's why we are talking in this case about an important notion called privacy budget. And that privacy budget is your computational budget. So the moment you deplete it, you can't compute on this data anymore.
Yeah. Okay. Thank you.
So you're welcome. So just from a user level, there are different ways in which you could interact with the compute platform. So you can interact via REST API, you could interact via a graphical interface, and then you could interact also via a Python module. So something that we call XOR-Py. So that allows you to essentially write high-level Python code that is going to make calls to the engine. So the first and the last one are better for developers. The second one is better for people, for users who prefer to use just predefined functions without writing any extra code. So let's look at some use cases first before we go further. So use cases that we have done with some of our partners and customers. So one of the use cases done with one of our investors is essentially use case done by JP Morgan. It's called double-blind trade matching. I'll explain it on a high level. Essentially, when you trade certain instruments like interest rate swaps, for instance, credit derivatives, they trade over the counter. So I take the phone, I call you, and I ask you whether we have this instrument. So typically that's difficult because I have to ask you what kind of position do you have, and you have to give me the list of your positions. So I'm learning a lot about your portfolio. The question is, can you automate this process so that you can do the matching just as you do it on an electronic exchange without actually revealing the portfolio of the counterparty? So this is what we did with them. So basically that that technology gives you a yes or no answer. Do you have this position or not? But it doesn't really give you information about the full position of the counterparty. And hence, you're protecting the trading strategy of that counterparty. So that's one use case that we did. And this is all good for trading instruments that are difficult to trade in general on an electronic exchange. And that improves the liquidity on these over-the-counter markets. So another use case, totally different, is fraud detection. So imagine that you have multiple banks, and these banks, they have different data for transactions that go through these banks, and then you want to try to classify automatically fraudulent transactions versus non-fraudulent transactions. So if you want, typically you do this with a classifier or some machine learning model. And the idea is that if you put data from more banks, then this model clearly becomes more precise. You're seeing basically on the right, essentially model 1 only gives you this ROC curve. Model 2 gives you a slightly better one, and then model 3, including data from 3 different banks, gives you that blue curve. So indeed, you are improving a lot. You're reducing the false positive rate a lot by using data coming from more financial institutions. Of course, transaction data cannot be shared across different institutions. So that's why you use secret computing here. Another use case is predictive maintenance. So we did this in France with Thales, and it's a very similar use case, except that they're building a machine learning model that essentially predicts the remaining useful life of various aircraft parts. So after a flight of a military aircraft, you typically take the readings of many sensors, and then you run a model that tells you whether the different parts are worn out and when exactly they should be replaced. So, of course, Thales doing this maintenance on military aircraft, for example, the Rafale aircraft. So they have to optimize this process, and they use artificial intelligence for that. Again, imagine that these planes are distributed across different military bases, across different countries. You can't obviously aggregate this data, so then you need secret computing just to get the aggregate analytics. That's the third use case in predictive maintenance. And the fourth one I'm going to talk about is in healthcare. So this is kind of similar, but for patients. So imagine that I'm a doctor and I want to understand your risk in 5 years from coronary heart disease. So I could get data from different data locations for the particular patient, or I could get a lot of aggregate data to just build my model that is going to predict the probability of a coronary heart disease in 10 years. So because this data stays at different locations, it could be different hospitals, it could be hospitals and health insurance companies, it could be also hospitals and personal devices for basically where you personal health devices or any other devices, any other IoT devices. So this data, of course, is very segregated, and it's subject to a lot of privacy concerns. In this case, what you do is you aggregate this data, but you aggregate it securely via the XOR computing, XOR secret computing engine. So here you could talk about horizontally split data, meaning that you put together more data with identical features from different hospitals, or vertically split data where you put together extra features that could potentially improve your model. So this is what we call the augmented heart disease analysis. These are the use cases that I spoke about here. You can see some of them appearing even in the press for INPHER. Very recently, we also won a competition from the Financial Conduct Authority in London about fighting anti-money laundering with this technology. where you need to aggregate a lot of transaction data across different banks. So let me give you now one of the main kind of features of our computing engine, what makes us different from other companies that are developing privacy preserving computing solutions. So I'm going to give you a kind of an extreme use case here, which is a realistic use case. And it comes from basically space exploration. So there was a collision of two satellites in 2009. This is on the left, you're seeing the Iridium 33 satellite of NASA. And then on the right, you're seeing the Cosmos 2251, that's a Russian satellite. So it turned out that they collided in 2009 with the speed of 11,700 meters per second. This was above Siberia, 789 kilometers above the Earth. And there were more than 2,000 debris as a result of this collision. So basically, as a result of that, it became even dangerous for the International Space Station that had to do special maneuvers to avoid colliding any of these debris. So why did this happen? And how did this happen? Let's take a look. So essentially, you have one trajectory, the green one, and then you have the red one, a totally different trajectory. So they belong to these different countries, US and Russia. They're never gonna essentially share this data for the trajectories. However, what these two countries both care about is avoiding a collision. So the basic question is, can I do a computation without knowing the trajectories, keeping the green and the red data as secret so that I could detect only the collision with a yes or no. So I'm saying these two satellites will collide or not, without actually revealing anything about the trajectories. So this sometimes is called conjunction analysis by satellite operators. But what is interesting is that in this case, if you do just an approximate computation, you may be off and you may not properly detect the collision. So this is one example where computing with very high precision, high numerical precision, is very important. Here's another one. So this is what's called detecting rare events. So what does it mean to detect a rare events? For example, I want to detect a fraudulent activity or any type of rare market event. Say that 1 out of every 10,000 bank customers performs a fraudulent activity. So if I build my classifier that always predicts negative, that classifier will have 99.99% accuracy. But this classifier is completely useless for that use case. You would agree with me, because this use case is trying to detect a rare event. So what's the reason for that? I mean, for those of you who know machine learning, it's probably obvious. So the accuracy here is 1, but the recall of that system is going to be 0. And hence, the score that gives the more precise, essentially, quality of the model, called the F1 score, is going to be 0. So you see that if my model is off by a bit, that could affect a lot the F1 score, and then I could get a totally useless model. So approximation is not an option here. You want to sort of compute the model as if you're computing it on plain text data. So what INPHER is doing is INPHER is specializing in computations that have very high numerical precision. So we're not allowing numerical errors here. Okay, now before I do that, I'm going to ask if you have any questions, and then I will kind of tell you a bit more lower level about the technology.
Can I ask a question?
I didn't hear.
Can I ask a question?
Sure, of course.
I have a question for especially the satellite collisions, because I'm not very sure about how it works in, let's say, the bank situation. But in the satellite collision, you mentioned that we could have it so that two different parties do not know information about each other, but they can still predict the collision, right?
Yes. So two different parties do not know information about each other's trajectories, but they want to predict a collision. They want to say, will there be a collision or not?
Wouldn't there be a need for a third party, a trusted third party that analyzes and decides what to share?
Ideally not. Ideally, it can be a decentralized protocol just among the two parties. Two
So
or
it's
more
possible,
parties.
right?
It's possible. Yes, it's possible.
Okay.
You will
Thank
see
you.
in a second even some basic hints on how this is possible.
Thank you.
Welcome. So we have to basically say a few words about this technology. So what is secure multi-party computation? So imagine that you have an image here. So this is an image. And now that image is private data for me. What I could do is I could actually secret share it with all of you in this room. So in this case, I'm showing you a secret share with two parties. So what is the secret share here? So the secret share is essentially generating completely random images that contain no relevant information on their own. These are called shares, and they're distributed to all the parties with the property that if you put them together as images, you're getting the entire image. So there is some correlation between these images, but every image on its own looks completely random. And in fact, if you take any proper subset of the players, then they will not be able to detect any information about the meaningful image. It's only by letting all the parties collaborate that you could get that information. Does that kind of make sense?
Yeah, it does.
You could play it with numbers also. If you take a secret number, I could secret share it with, like, let's say among 5 people with 5 distinct random people. And then when I add them together, I get my secret number, but no proper subset is gonna give me any information about the number. So that's good. So
sorry, can I intervene again? In this case, could someone, an outsider, make the system create all of these random pictures and then add them later on, like I guess ciphertext and plain text attack at the same time? So you feed the system and you ask for the random images. Can you, after you get the images, can you still get like the idea behind the algorithm?
So I didn't fully understand the question. What is the external party doing exactly?
So let's say that I do not know what the code is, but what I do is I ask to access the algorithm to create my own images. And then at the end, I end up with different images that when you add them up, they give me the answer, right? Can I analyze this post-processed pictures to get the algorithm?
So you're talking about which algorithm, the compute algorithm or the secret sharing algorithm? It's important.
I guess the secret share, the one who generates the pictures.
The one who generates the pictures is, in fact, the party that owns the data. So if I own this data, then I simply generate the secret shares and I distribute them.
Yeah.
Okay.
That's how it will it works normally. Yep.
So
does that answer?
Yeah, it does. Thank you.
Okay. So you will see now in a second what happens. So imagine that we want to multiply 6 times 7. However, 6 belongs to one of these two clouds and 7 belongs to the other one. And they're not supposed to be revealed to each other. So suppose that 6 belongs to the green cloud. Then the green cloud is going to generate 2 secret shares and it's going to secret share 6 among the 2 clouds, 2 or more clouds. Then the red cloud is going to secret share 7. So you get these 2 secret shares in the input. Now, what you are allowed to do, suppose that you want to multiply 6 times 7. So what do? So you start computing locally. You do some communication, but that communication should not reveal anything about 6 or 7. And then on the output, you could get 2 secret shares. So as such, you either put them together or you continue the computation, taking those as input. So if I put them together, I get 42. That means I reveal the result. If I don't reveal the result, I just take these 2 secret shares as a collective variable or collective value, but secret share, and I feed it into the next multiplication gate or addition gate. Now imagine that this operation were addition instead of multiplication. You would see that this is easy, right? All I have to do is just add locally these 2 shares, and I get secret share for the result. But multiplication is much more tricky. So addition is easy because your secret shares are additive, so it's a compatible operation. You don't need any communication, but multiplication is tricky. And this is where kind of random numbers come into the picture. So like the algorithm that does the multiplication, that allows you to do the multiplication, is called Beaver Multiplication. And here I'm kind of writing it more abstractly with groups, but you don't just think about real numbers if you want from the moment, because we very often operate on entire tensors and not only on groups. So what's happening is you have X and Y. These are the 2 inputs, and these are secret inputs. They're secret shared. Your goal is to compute X times Y. Or secret shares, more precisely secret shares for X times Y. What do? So you have an offline phase that essentially is going to do the following. So it's going to generate 2 random values, lambda and mu, independent of each other, independent of X or Y. So they're random values. And then imagine that I compute lambda times mu. So I have lambda, mu, and lambda times mu. And those are secret shared among the participants. So these values are called masks for the moment. Just take that word. So here is an algorithm that you could run. Now, I know that party 1, computing party 1 has 1 share of X and 1 share of lambda. So what will happen if I just locally add my shares of X and lambda and reveal them to everybody? So that means that everybody will be able to compute the value of A, which is X plus lambda. So that's a publicly known value. The green value here means publicly known. Now, if X and lambda are if lambda is random and independent of X, obviously this value here is going to mask completely X. So no information about X will be revealed if, say, lambda is uniformly random and uncorrelated with X. If I do the same with B, and now what happens? So what happens after that is I'm saying, now suppose that I do a computation, X times Y. So how can I rewrite my X times Y? I'm removing X and Y, I'm substituting essentially, I'm writing X as A minus lambda and B minus mu. So it's a very simple algebra. And what you see is that you have a 4th term in the Beaver product. So the first term is publicly known. The second term, I have a value lambda that's secret shared and a value B that's public. So this is very easy to compute. If everybody knows B, they just multiply their secret shares by B and they get a secret share for lambda times B. Same for A times mu. And now I've assumed that lambda times mu has been secret shared. So essentially what I did here with this really simple, like 5th grade trick is I've managed to linearize my product. So now it's become a linear function and I could compute that easily without any extra problem or communication. Right, so this algorithm is called Beaver multiplication. Now, if you look at it, what is important to know is that you need to compute. So the problem, we've kind of moved all the difficulty of this computational problem to the generation of lambda mu and lambda times mu, right? So what's the obvious way to generate this lambda mu and lambda times mu? I mean, I could simply take a random number generator, generate lambda, generate mu, generate lambda times mu, secret share those and send them to all the parties. However, for that, I need to use a trusted party, clearly. So that party should not see your data, because if the party sees some of the secret shared inputs, then that party will potentially know basically the secret shares and will learn information about X. So that party, whoever party computes that correlated randomness, lambda mu and lambda times mu, that party should be disconnected from the computation during the online phase, during this phase. Do you have any questions about, so this is a very simple kind of sound protocol, but that's the tricky part, to realize that essentially you need this correlated randomness. So you need to produce lambda mu and lambda times mu.
Yeah, it looks clear. Yep.
Yep. Now
I have a question.
Sure.
So is this Beaver triplet multiplication that you use for the application that you showed previously?
So almost every secret sharing protocol uses Beaver multiplication in one way or another. The way we use it, so we do use Beaver multiplication as well. We use it on tensors, and we use it also we use it in a special way to evaluate also nonlinear functions, so non-arithmetic circuits.
Okay.
Because, yep.
So if you use it that way, how do you do to make training on neural networks and stuff? Because you have to generate millions of Beaver triplets to make it secret.
Yes, so that's exactly the point. We have a lot of tricks to optimize this process.
Okay.
Generation and also communication, because here, if you have a matrix that's 50 million by 100, then you have to generate a mask for this matrix. So that's very expensive. You can't just broadcast it on the network. So let me tell you the two ways in which you could generate this randomness. So the first one is centralized, and as I said, it depends on a trusted party, but then you have all these extra questions that you have to care about. Verification. So how do you verify that the party is trusted? How do you verify that it gives you randomness from the correct distribution, that it doesn't give you any bias in the randomness? So obviously this is preferred because this scales, and essentially what you do is you could do a lot of optimizations, including massive parallelization. Now the other type of randomness that you could use here is more cryptographic, and it's less scalable, but it gives you a stronger security model in the sense that it removes this trusted party. So it's called decentralized randomness, and it uses special cryptographic techniques that are known as oblivious transfer. I'm not going to enter into the details here. I'll just say that this is on a cryptographic level what is used. So what it enables you to do is it enables you to achieve what's called active security models. However, you can't do any meaningful machine learning with this because basically of the scalability issue. So this is very slow. You could do small computations with active security, but the moment you want to scale your computations, you have to use the centralized one. At least up to now, there hasn't been any really scalable, efficient oblivious transfer protocol. So that's an open question in cryptography, how to make techniques such as oblivious transfer scalable. Okay, And now, finally, before I wrap up my talk and ask you for more questions, so you see, this problem is both cryptographic and also it's a problem about generating randomness. So how do we collectively in this group generate a triplet lambda mu and lambda times mu, so that no one knows the values of lambda mu and lambda times mu. We only hold secret shares, and even no proper subset of us knows anything about the values of lambda mu and lambda times mu. So this is cryptographically possible. That's what I wanted to say, and these techniques such as OT, they enable it. So now finally what I want to do is I want to tell you how we actually do computations that are more, how do we represent real numbers. If you want to compute with real numbers, you typically talk about floating point representation and fixed point representation. So in the floating point representation scenario, the addition is the one that's more inefficient. So floating points are adapted more, floating point computations are better for multiplications. That's why you would see a lot of the laws of physics written in multiplicative form. The fixed point representation suffers obviously from the overflow issue. So that could blindly basically destroy your result. What we did as a company at first was we essentially designed a certain type of fixed point arithmetic using floating point arithmetic on the back end at each party. That means every virtual machine is going to use floating point backend, but the result of the computation collectively on secret shares is going to be essentially simulate fixed point arithmetic. So there are several pros and cons about that approach. So first of all, the overflows essentially, in this case, are not going to destroy your result. Also, you need to support floating point arithmetic with large numerical window, but that's supported on some hardware. On the cons level, you have a small impact on security because you don't have uniform distributions on the real numbers, and you have to use what's called statistical masking instead of perfect random masking. So your masks are essentially drawn from a Gaussian and not from a uniform distribution, which does not exist, right? So basically, what is happening now? So essentially, if you think about that simple example from a statistics point of view, imagine that you have two values, plus and minus 1, and you're trying to distinguish them. If I mask them with a Gaussian that is too spiky, I'm not doing a good job masking these values. So if, for example, my standard deviation is 1, then I have these two distributions that can be distinguished. If, however, my standard deviation is 100, then these two distributions become really close from a statistical point of view, the statistical distance point of view. So you see, in order for me to do a better masking statistically, what I have to do is I have to use standard deviation that's really large, much larger than the actual values. So that's very bad because that's very bad because as you aggregate more and more computations, this standard deviation grows a lot, and then your numerical window grows a lot. And at some point, you start overflowing. So what we have to do is we need something else in order to solve this problem so that we can make this scalable. So here are some disadvantages. So memory overhead, obviously, computational security versus information theoretic security. You never achieve information theoretic security with this approach. So what we do instead of using floating point backend, we are going to use integer backend. And how do you do how do you represent real numbers? So I'm going to represent them using integers. And I know that a floating point representation has a mantissa and an exponent. And this mantissa is typically a rational number, so I could scale it to be between 1/2 and 1 if x were public. And then I could compute what my exponent is. So it's another integer. Now, in our case, x is secret. So what can I do? I could basically only approximate what the exponent is, and I could secret share the mantissa. So essentially, if you do that, then you need estimates on the exponent, and you need some estimates on the mantissa. So then basically what we do is we design this floating point arithmetic using secret shares for these integers, for the mantissa values. And by knowing some information on the size of the integers, on the tau, then we could perform our arithmetic. So obviously, as usual, the addition is going to be more difficult than the multiplication. Now, I'm not going to tell you more about that because it gets very technical, but essentially we define these plain text classes and we statically estimate the parameters for these plain text classes. So we keep the position information of the position of the most significant and the least significant bits. And before we execute our program, not in runtime, but statically, we estimate these parameters. So this is what essentially our compiler, special purpose compiler for multi-party computation is doing. Okay, so essentially, I should say probably a few more words on that before I wrap this up. But you have these classes of plain text values, and then you need to implement appropriate casts for them. So how do you cast a value from one class to another class? So this is also an operation that's done on in an offline and online mode. And the compiler has to decide and insert these casts. So what we've developed as a company, we've developed a compiler that takes an entire program and then sets the appropriate distributions for random number generation that could perform you a secure multi-party compute solution. I think I'm going to stop here and ask you for questions if you have.
Okay, thank you very much, Dimitar. Very, very interesting, really. I let the audience start in case they have questions. Okay, maybe ask a couple of questions. So the random numbers that you need are actually, they go beyond actually splitting between the multi-parties, the data set. You really use them to build up the secret share, right?
So
so you need a huge volume of random numbers.
So you need a huge volume of random numbers. That's right. Exactly. For a massive computation, you need a lot of random numbers. The point is that you don't communicate all of them explicitly. You essentially could communicate some seeds, and that saves on your communication.
Okay.
So it's always a trade-off of how much you generate in the offline phase versus how much you could generate on the computing nodes.
And then again, it's a high level question, but the answer might be obvious. But if you compare your approach to the homomorphic encryption, which are the advantages and disadvantages that you see?
This is much more scalable. that approach is much more scalable. So in homomorphic encryption, you have the data encrypted on the cloud, and you operate on that encrypted data.
Yes.
So here we're talking about models that compute 50 million data points and hundreds of features. So regression models. And that is possible in just a few hours of computation. So with homomorphic encryption, that's very much orders of magnitude away from the current state of the art.
Okay, I see.
So you could use homomorphic encryption for certain small operations, but not for scalable operations like this.
Can I ask you a question on that?
Sure.
Please.
So you say that homomorphic encryption is less scalable, but as far as I know, the state of the art on secure multi-party computation doesn't go beyond 5 parties or so, because distributing and the communication load from exchanging all the arguments becomes so noticeable that the parties are no longer computing, but are just communicating, and most of the time is spent on communication. So in that sense, homomorphic encryption could be more efficient, even if the data takes more time to be computed. At some point, the computational load will become worth rather than the exchange, the communication exchange, right?
Well, I mean, if you have, it depends on how you see it. It is true that in a multi-party compute scenario, everybody computes with everybody else. But imagine, for example, this technology that's called federated learning. So there you have clients communicating to a central server. In that case, you do not have communication between the clients. You could have as many clients as you want. So essentially, they serve different purposes. So obviously, in a fully homomorphic encryption scenario, you have to encrypt your data and to send it to the cloud. So if your ciphertext is gigantic, that's also communication overhead. The problem is that you can't even really start computing scalably on the first place. Does that answer your question? So for example, in a multi-party compute scenario, during the computation, you have to have communication. But in an FHE scenario, you're not talking about communication at all there. You're talking about just computation on the cloud. Okay. But that is beyond reach these days.
Okay. Okay, thank you.
Yep.
Okay.
Can I add the last question?
Sure, Jose, go.
Sorry, I'm just, it's my PhD topic, so
of course, I guess so. I mean,
it's interesting for me to get.
It is also for the audience.
Yeah. So, regarding the zero knowledge proof, how do you make it scalable when you have to make so many of them? So
what we're not computing on the entire data. We do basically a subsample, and so then we verify something on that subsample.
Okay, thank you.
So again, you have a probabilistic. Huh?
Yes, it's a probabilistic.
Okay, thank you very much.
So yes, please.
So you could scale that computation. So this satellite collision is essentially more like physics computation. So I mean, it is just given as an example in the, obviously INPHER as a company isn't really doing computation on satellite trajectories, but basically you could scale it to some.
Yeah, because
so
maybe
we
Daniel,
have not done. We have not.
Sorry, maybe you should tell why you're so interested. Me personally, I know, I believe, but it would be nice if Dimitar knows as well.
That would be good. Yep. Aha. So you are interested in, so you have several trajectories and you're trying to, and they're secret, basically.
To some extent, they're secret. They
They cannot
be parameterized. Yeah.
Yes. So if you can't, I mean, you probably in the satellite case, it all kind of parameterizes to some extent. Like you know the velocities, you know the you know the physics in a fairly explicit manner. Here I believe when you talk about trajectories that you don't know, then you need to keep track of a lot more data. So maybe that problem becomes more intractable. But so do you need this for basically commercial applications? What is that? Where is this coming from? Yeah. Right. I would need to see more details on the computations here to be able to answer that question. Yep.
Now you're in contact, Daniel. It's also a good outcome of the event. Okay. Look, let me thank again Dimitar. It was very interesting. You trigger a number of questions, which is a good indication usually. And it's certainly high level what you're doing, both in terms of mathematics and in terms of implementation and use case. And actually the number of use cases that you quoted is telling that you're doing well. So we keep in touch. I'm sure people will get back to you, and we will let you know also the outcome of the hackathon, so that at least you can browse whether there is something interesting.
Thank you. Thank you very much.
Thank you very much.
Good luck to all the participants.
Thank you also to Claudio, who got us in touch and who's actually the actor behind the scene. And if it's not a problem for you, Dimitar, could you share the slides and we keep for the records? You just send them through the email. And
yeah, we can share some of the slides.
Okay, yes, just purify them as much as you want.
Exactly.
Public what you can.
Exactly.
Okay.
Sounds good.
Thank you very much.
Thank you, and good luck on the hackathon.
Thank you. Thank you to all of the participants, and we'll be back actually at 5 p.m. for the final speech of the day. Have a good afternoon.
Bye-bye.
Bye-bye.
Bye.
Massimo. Bye-bye.
Bye.
Bye-bye.